Hi y'all, this is a nice reaction rate problem. They give you 3 experiments and they give you these initial concentrations of the reactants and they give you the rate that you get. So determine the order of reaction with respect to H2. How do you go about doing this problem? Well, think of this as as a real experiment. If you want to know how H2 concentration affects the rate of this reaction, what do? Well, you change the concentration of H2 in an experiment, and then you do another experiment where you change the concentration of H2, and then you compare the rates that you get. But when you do those experiments, you really need to leave Cl2 constant. You have to have plenty of Cl2 there, and you can't be touching its concentration. Why? Because if you change both H2 and Cl2, you have no way of knowing what effect H2 had on the rate. You have to keep everything the same except for H2 and change only H2. And where has that happened? Here's H2. Here I have 0.0. Oh, sorry. Where has that happened? Here's H2, here's Cl2. Here, Cl2 has been kept the same at 0.0005, 0.0005, right? So here we have a nice setup for an experiment. These two have changed, and these two have not changed. What was the change here? Well, the change here was this number divided by this number. That's 2, so we have doubled. So I'm going to put times 2. From experiment 1 to experiment 2, we've doubled the H2 concentration. What has happened to the rate? Well, when I figured out that this got doubled, I did experiment 2 divided by experiment 1. So let me see. Did the rate also get doubled? When I double H2, if the rate got doubled too, then that would mean that H2 is first order. If this rate got quadrupled, then 4 is 2 squared. See? So this 2 right here, if that 2 squared is 4. So if this represents a quadrupling, then I know that the rate is 2. It's a second order in H2. All right, so let's have a look. On my calculator, I see, well, first of all, I see 10 to the minus 12, 10 to the minus 12. These are the same, so these cancel. On my calculator, I do 3.64 divided by 1.82. I invite you to pull out your handy-dandy calculator with me. Yes, the scientific one. Where's mine? Aha. Yes, that's right. You're the scientific one. Even though this one does not require a scientific calculator. 3.64, where's the divide sign? Divided by 1.82. 2! OMG! This is not 4, this is 2. So from experiment 1 to experiment 2, I increased the rate by a factor of 2. Caused by an increase of H2 concentration by a factor of 2. That means that the order of H2 is just 1. That's a first order reaction. Okay? First order reaction. What about with respect to Cl2? Oh, okay. Well, let's just do this whole thing again, but with looking at Cl2 instead. Okay? So here we have Cl2. Here I have a change of Cl2, but where are we keeping H2 constant? Remember, we've got to keep something, keep everything else constant. Oh, here we are, constant. So here, I see that experiment 2 is the larger number, so just for convenience, I'm going to do experiment 2 divided by experiment 3. I know that 500 is double 250, just mental math, so experiment 2 divided by experiment 3, I should just do it this way, right? From experiment 2 divided by experiment 3, that's a multiplication of 2 there. What about this? From experiment 3 to experiment 2. So experiment 2 divided by experiment 3, this is also times 2. How do I know that? Because I'm doing experiment 2 divided by experiment 3. 3.64 divided by 1.82. It's the same math. I mean, this is such a nice little problem here. It's such a kind-hearted problem. So 2 here, that 2 to the first power equals this 2. You see that? And this is the order of the reaction. Okay? Okay, good. What is the overall rate law? Well, the overall rate law is rate equals, it's always the same thing, you know, it's always rate equals some rate constant times the concentration of one reactant, and then the order to the power of 1 times the concentration of some other reactant, and then the order to the power of 1. Okay, now it's that order, it's this order that is sometimes different, you know, but, you know, if it's really to the power of 1, you don't have to put it, you know, it's understood, so you just put that, and that's the rate law. Cute, right? Right, the units of the rate constant. Oh, I love these. This is so absurd. Okay, the thing is, the rate has to always be in molar per second. That has to be the rate. So it doesn't matter what all you have over here. These guys are, here, let me do a different color. Whenever you have square brackets, the square brackets means molar. Square brackets means molar. It doesn't matter how many things you have out here. You have to create your own units for K, the rate constant, so that you end up with a total units of molar per second. You see, in this case, I have molar squared, right? So the units of K are going here. Equals. The units of K are going to be molar over seconds. Why? Oh, I'm sorry. That's wrong. That's wrong. The units of K are going to be 1 over molar seconds. Why? Because you just have to make up whatever K units you can to get molar per second as the rate. So here I have made up 1 over molar seconds. The reason I made it up that way is so that I could cancel these molars and I get molar per second. You see that? Molar per second. Molar per second. I know you don't believe me, but just verify in your textbook. This is how it's done. It's that ridiculous. Right. So anyways, K, the units of K, the reason why the units of K are like this is because the rate, of course, is molar per second. It's like when you drive your car, it's miles per hour or kilometers per hour, you know? You're never going to drive like miles squared per hour, you know? But here, sometimes you're going to have a second order reactant here, or maybe even a third order reactant, so that you're going to have to fudge your K units so that you get molar per second. So anyways, predict the initial rate of the reaction if the concentration is 0.003 molar, and the initial concentration of chlorine is 0.0005. Okay, so they just want you to solve for the rate. Okay, so this is a two-part problem because in order to find the rate, you use this equation, of course, right? But they give you H2, right? There it is, and they give you Cl2, right? There it is. But they don't give you K. So you're like, how am I supposed to solve this equation? How am I supposed to get the rate if I don't have K? Well, they want you to get K by yourself. They want you to get it from here. So you just pick one of these, right? Because this is ostensibly an AP test, right? So you just pick one of these and you say, okay, rate equals K times this times this. So I solve for K. You want to see me do that? Okay. I'm waiting for another page. This is supposed to give me another page. You know, I just did this thing and it's supposed to give me another. Wow, this is taking a long time. Page? Can I have another page? Yes, thank you. Okay. So here, I'll show you Glenn doing this. So I'm going to pick reaction number 1. All right. So you know that rate equals K times H2 times Cl2, right? This is what we just found, yeah? So that means the rate is this. So it's 1.82 times 10 minus 12 molar per second, yeah? I draw this little underline underneath the M because you're supposed to make it italics, but here, just so nobody gets confused, I'll just make it italics. Molar per second, yeah? That's the rate, and we don't know what K is, and the hydrogen concentration is right there, you know? It's 0.00100 molar. And then the chlorine concentration is right there, you know? It's 0.0005 molar, yeah? And then you're going to solve for K. Okay, ha ha ha. Solve for K, okay, ha ha ha. Alright, so 1.82 times 10 minus 12 molar per second over this. Okay, it's 0.000, and then there's 3 decimal places here, so 1, 2, 3, 5. This is, that's too many, right? No, that's right, okay. That's molar times molar is molar squared, okay? So, K, I do this on my calculator. Do I have to do this? Okay, I'll do this. So, 1 point, you can do this too, you know. You can get your calculator and do this too. Times 10 to the minus 12 divided by point, how many zeros am I going to get? 6 zeros? Good grief. 1, 2, 3, 4, 5, 6. Okay, so I get 3.6 times 10 to the minus 1, 2, 3, 4, 5, 6. Minus 6. How many significant figures? 3 significant figures. Okay, so it's 3.64. So I get K equals 3.64 times 10 to the minus 6. What are the units? We already determined the units. Okay, we'll do it again. 1 over molar seconds. So you could, to be elegant, you know, you go molar to the minus 1 power, second to the minus 1 power, because that's the same as saying 1 over molar seconds. You know, it's just nerdy. So there we go. That's the K. Now, if you were doing this in the lab and you were actually doing an experiment to find K, you wouldn't just pick one of these. You wouldn't just pick one of these experiments. You know, you wouldn't just pick that one or that one or that one to find the K. No, you would graph this, and then it would make a line, and then you would do some math to make it make a line, and then the slope of the line would be the K. You know, so that's how to find sort of an average K. Or if you don't feel like graphing, you would find K for all of them. You know, you would find the K for this, find the K for that, find the K for that, just like what I did for number 1, but you would do it for all of them, and then you would find the average K. You know, and that would be the K that you would use. But this is not a real lab experiment. This is you taking the AP test. So in that case, you just pick one experiment and you find K like that. Okay?